Okay, so today, eigenvectors. So, yay, eigenvectors. So why eigenvectors? So like some of the other things that I talk about in this class and in the neuroimaging class, it's a very general, sort of useful way of doing simple math, eigenvectors. And when I never properly took a linear algebra course, but I started one, then I had an appendectomy and dropped out. And I remember they talked about eigenvectors, and I sort of went through the equations, but I just couldn't see like how I needed some kind of use for it, being sort of a biologist originally. And so what we're going to talk about is trying to analyze those Hebb weight update equation using eigenvectors. And in the process, we'll hopefully see how doing eigenvectors can help understand a differential equation or a system of differential equations, because that's actually what the update rule is. It's a differential equation. It says a change in something equals something to do with that something. It's a very simple differential equation. The derivative of something equals something that involves not the derivative of it. And so let's start off. And so what I was trying to do last time in the main class was just sort of get some intuitive idea on why is orientation selectivity an expected outcome of particular correlation patterns. But what we want to try to do now is, can we make a catalog of all the different possible outcomes given a particular correlation pattern? And so that's to sort of like treat it a little formally. And so we'll start off with our the equation, which was the weight between, and this goes along with this picture. So here's the output unit J, and then here's an input unit, one input unit I, and here's the weight Ij, and then there's another input, and this guy is weight weight from other to J. One more time. Okay, weight from some other unit to output unit J, and then here's some input other. And there's lots of other inputs, 1,000 other inputs. Okay, so the simple Hebbian learning rule that we got from the absolutely simplest possible Hebbian update rule, which was just input times output, was a constant, which I didn't annotate last time, plus 1 over the number of inputs, because of we said when we brought the input I inside the summation, and then now we sum over all the other inputs, and what do we sum? We sum the correlation between the current input and an other input, so the correlation between these two guys. Then there was another constant in there, so we stuck another constant in there, plus K2. I'll explain what that is. And then that was multiplied by the weight. So the weight from this weight here, this other weight from other to J. And we got that just by saying we have a Hebbian learning rule. It's input times output. The change in weight is input times output. But output is in fact the sum of all the other inputs. And so if we just substitute in that, then we see that we end up with what's really driving it is the correlation between each pair of possible inputs. So that was the first equation, and we had the constants I didn't mention. This one is decay. So you might have your weights might just sort of decay. It could be positive or negative, but they might just get a little less strong every time, no matter what, even no matter what you do. And then this one is set no change point for correlation. So so those just allowed Linsker to play around with different parameters. Now, what would these things normally be done by in real life? There would be like, constraints on how many vesicles can you put into a synapse, all different kinds of, adjustments that neurons are making. It would be literally 1,000 different parameters in a real neuron, but we're just really simplifying it down here. And so that's the that's the equation, and you could simulate that equation. What you could do is you could basically set up a big network, apply some sort of correlation pattern to it, and update the weights and keep updating the weights. And we described that procedure. But if we try to look at this just a little bit more abstractly, and try to sort of simplify out, just find out what is the main driving force of this. And that's often what you do when you apply math to some situation. What you want to do is you want to somehow, the mind can't think very complicated math. And so it has to be math that just has 3 or 5 parts in it. And that's already got too many parts in it. And so how can we sort of really simplify that down? So we'll do it in a couple stages. So let's first start off just considering one weight. And so the first thing we'll do is we just get rid of, since these units don't interact with each other, and we've only got one output unit, we can just forget about the J. There's just a single output unit. We're not looking at different output units, just one. And so what this says is basically one weight, and then we've got some constants in here and number of inputs. Let's just throw all those out and just consider basically what is this equation. So this equation basically says we've got that thing, which is basically a vector. So this is the correlation between this unit and all the other units. So that's a vector of numbers. It's a vector of numbers. And when you have a summation and two things in there multiplied by each other, that's like a dot product. So that's like a dot product between two vectors. And what's the other vector? Well, the other vector is this vector of weights. So then there's a whole bunch of other weights. So there's correlation with all the other inputs, and then there's a whole bunch of weights for all the other inputs. And so that's a vector of weights. And then we're doing a dot, this equation up here, the summation and multiply two things, is basically just a dot product. And what is a dot product? You just take two vectors, take each of the corresponding components, multiply them by each other, and add them all up. So that's basically, so now we've simplified our equation, sort of math style, so now we've only got 3 things in the equation. And so this says one weight is basically equal to a dot product between these two vectors. And when you do a dot product between vectors, you end up with a number. And so the change in a weight, the change in one weight is basically equal to this dot product. So this guy, so this is, change in one weight. Okay, so that's good, but that's only one weight. And so what we really want is all the weights. How can we describe the change in all the weights? So for that, we're going to have to scale this thing up, which is just one weight, up to an actual vector, so that has a whole bunch of different weights in it. And so what we want is, how can we add in whatever we need on the right side in order to end up with the change in the weight vector, so the change in all the weights. So we want to somehow sort of sum across all these different weights, or consider all those different weights. And there's basically an equation just like this for each of the other weights. And so what we can do is, it turns out we can just get a matrix. It's just a bunch. You can sort of think of it as just a whole pile of vectors, also known as a matrix, so a square matrix of correlations. But then what are we doing? We're just still, there's only one weight vector, and so we're multiplying that times the same weight vector. So now so this was, vect. So this was, this guy's a scalar, so that's just a number. So a number equals a vect times, so this guy is a vector, and this guy's a vector. Okay, so now what do we have here? So let me just draw that one down a little bit lower so I've got some room to annotate it. So this is the change in the weight vector now equals this matrix of correlations, because we need a different. So why do you need a matrix? Well, consider this vector up here. This vector, or the one between the current unit and some other unit. So you go, the current unit, this one, current unit, this one, current unit, this one. So correlation between this guy and everybody else. But if I go over to a different weight in the weight vector, now I've got to have a different set of correlations, which is the correlation between this guy and that one, and this guy and that one, and this guy and that one. So we'll need essentially the correlation between every pair of inputs, whereas this thing is just the correlation between the current input and every other input. So that's why we get the matrix. So now we've got this matrix of correlations times the same weight vector. So that square is supposed to mean, like, just to remind you that that's a matrix. And so this is change in all weights. That's the weight. That's what the weight vector means. Equals matrix of correlations. So every matrix of correlations times the weight vector. All weights again. So that's our simple equation. So now, whenever we see an equation like that, we have some useful apparatus to apply to it. And so what is that? Well, what you're looking at here, whenever you have sort of a vector equals a matrix times a vector, then you just have a simple system of linear equations. So what does a vector do? What does a matrix do to a vector? So it doesn't do very much. So if we take a matrix, like matrix A, and we multiply it by vector x, and we get another vector, that's just the same thing except swapped around. What does that mean? What can a matrix do to a vector? And it can't do too much to a vector, but basically what it can do is it can, so if we've got a vector, so here's a vector, say that's our vector x. There's our vector x. And so what can a matrix do? Well, it can basically, so matrix it can basically scale or rotate, or both. So if this is our starting vector, when we apply that matrix, we'll get another vector, say that's the B vector. So it goes up to there. And so what did it do to that vector? Well, it rotated it a little bit, and it stretched it. It could just stretch it, it could just rotate it, or any combination. So it could basically sort of move this the matrix has the potential to move this vector anywhere else. Of course, if you have another vector, it's going to get moved to a different place, which will be related to the different place that this guy got moved to. And so that process is called of having a matrix, moving a whole field of vectors somewhere, is called a linear transformation. So that's a linear transformation, and it's actually more restricted than you might think. So the kind of things you can do to vectors, you can basically scale them all or rotate them all, but you can't. There's not a lot. You can't cause any bending actually in the shape of something, and we'll sort of like come back to that. So now. So that's basically what a matrix can do to a vector, and that's basically what's going on here. We've got a vector here, which is our change in the weight vector equals a matrix operating on the current weight vector. But one thing you notice is it's kind of recursive. So if we change this weight vector as a result of doing this, the next time around we have to come back and put a new weight vector in. So the weight vector is going to be constantly moving. Every time we update this equation once, like calculate what the change in the weight is, then we've got to add the change of the weight onto the current weight, and now we've got a new right-hand side, and then do it again. So that's really what we're trying to get an intuition for. What happens, what are the patterns that you're going to typically get when you reapply this equation, operate this differential equation. This is a differential equation. It says for a small amount of time, this is how the weight vector is going to change. And how is it going to change? It's just this matrix operating on the current state of the weight vector. So that then you start to get a feel for why do eigenvectors somehow relate to differential equations? And how does that all relate to Hebb? So one of the very valuable things you can do with a matrix is something called the eigenvalue problem, or the eigenvector problem. What do they call it? So now we got the eigenvector problem. Solve. So we can solve the eigenvector problem. So what is an eigenvector? So an eigenvector is a very simple concept, which is that if you have a matrix and you operate it on a vector, it's going to possibly rotate it and scale it. And what the eigenvector problem is solve this equation that I'm writing down. Just solve this equation for x. And what does that equation mean? So let's look at that equation. So lambda is just a number. So this equation says a matrix operated on a vector, and it might have scaled or rotated it. And then what I want to find is a vector. So this is the unknown. So solve for x. What I want to know is find me a vector that only stretches or shrinks when this matrix operates on it. So that's the meaning of the eigenvalue problem. So find a vector, take a matrix. So you've got all different kinds of matrices. So you take a matrix and then solve for a vector that when the matrix does whatever it does to it, it only expands or contracts. So that's geometrically what an eigenvector is. And it turns out there's as many eigenvectors as there are dimensions in the matrix. So if the matrix is 3 by 3, then there'll be 3 eigenvectors. And they'll be perpendicular to each other. So you can also think of eigenvectors as defining a coordinate system because of the fact they're perpendicular to each other. So it's the same thing that you do for principal components. You sort of start off with some data and you find a new coordinate system for it. Same thing you would do for diffusion tensor imaging. You're trying to figure out what direction the diffusion is going in, and you solve the eigenvalue, eigenvector problem and figure out what is the main direction. Now, so basically this thing, one of the solutions here is an eigenvector. And then this guy is called the eigenvalue, and there's an eigenvalue for each of the eigenvectors, and that means how much stretching is going on. Or shrinking. Could be shrinking too. Or it could just be 0. It could be 1, not 0. It could be 1, which means it doesn't shrink or stretch. That's possible too. So, and then we can order the eigenvectors. This is an important point. We can order them in the order of which one stretches the most, and then go perpendicular to that guy and say, what's the one that stretches, what direction do we have to go to find the one that actually stretches the second most? So that's an important point, is that it sorts the eigenvectors into like which coordinate causes the most stretching. And that's kind of what we want to know, because, what pattern are we going to get? So let's just draw out what an eigenvector. So this basically was caused, caused by the A matrix. So that guy right there. So what an eigenvector is something. We take a matrix, any old matrix, and then what we do is we say, let's find a vector. We don't know, if I operate the matrix on this vector, say it rotates it a little bit. And so what we want to do is find a vector, which vector, this is just in 2D, which vector is the one that only stretches it. Which vector is the one that the matrix only stretches. So basically, what that means is if we have an eigenvector, then when we operate the matrix on it, the only thing it does is it just stretches it or shrinks it. And then once we've found that first eigenvector, which causes the most stretching, then we look perpendicular to that guy and find the eigenvector that is the next most stretching. So something like that. So that's what the eigenvectors are. They're the directions in space that when vector directions in space that when you operate on a vector with that matrix, it only stretches. And there's as many of those as there are dimensions in the space. So this is a two-dimensional space, so there'll be two eigenvectors for a two-dimensional space. So what is that useful for? So let's just consider a simple linear transformation. So we'll just draw out a simple linear transformation so you can see why we want to know why the eigenvectors are going to help us get an idea of what's going on here. So let's draw. I drew it too small last time, so nice and big this time. Before I start, let's just go back. We should have started off with, what are we trying to figure out? So we jumped into the math a little bit too soon. So here's what we were trying to figure out. We were trying to figure out we've got a unit up here, and then we've got these units down here, and they have, they have center surround correlation. So here's, 3 units with center surround correlation, and they're all going up and projecting up to this guy. And what is that? Well, this thing here is a weight vector. And then what we're doing is we're applying a correlation down here. So down here we're applying some kind of matrix. We're applying a matrix of correlation. So that guy's a matrix. And what does that mean? It means like, here's a pattern of activation in which the correlation between each point, each possible pair of points in this input map have a particular value, and then we're trying to figure out like what weight pattern are we going to get. So that's basically what we're doing. We're applying a correlation here, matrix of correlations, and we're operating on the weight vector, and then it's causing changes. And what we want to know is after a while, after a bunch of changes have occurred, what is the weight vector? So that's really what we're after. And the problem is, depending on what you start off with, depending on like what the random weights are at the beginning, you might end up going off in different directions. And so what we want to do is to be able to have a whole catalog of what are all the possible things that could happen to this weight pattern after you run it for a long time. Okay, so that was, I should have said that at the beginning. That's what we're trying to figure out with doing this math. So let's just look at a very simple case of a linear transformation. So here's a simple case of linear transformation. So imagine we have a circle, just a simple circle. Okay, and the circle will allow us to define a whole bunch of vectors. So here's there's a vector, and here's a vector, another vector down here. Okay, so this linear transformation can sort of operate on a vector anywhere, but let's just consider operating the linear transformation just on a circle of vectors, because that simplifies things a little bit. So say we have a particular linear transformation that essentially just stretches, say it doubles the length of the circle in this direction. But say it doesn't do anything, so this is like a typical linear transformation. Two-dimensional linear transformation. So basically what it does is it stretches the circle out in that direction, and it doesn't do anything to it in this perpendicular direction. So here's the perpendicular direction. So if we took that matrix, the matrix that did this, the A matrix that did this, and calculated solved this eigenvalue problem, we'd end up with two x's, and one of them would be in this direction, and another one would be in this direction that would be perpendicular to that first one. So now, if we look at what the matrix did to this vector, what is it going to do? Well, it's just going to, I'll draw it in red, it's just going to double it. So that means that this guy would have a eigenvalue, and how much stretching is there, of 2, because it doubled that vector. And then if we look at a vector in this direction, what does this matrix do to it? It actually doesn't do anything to it. So this guy, it just keeps it the same. So now that guy has an eigenvector. The second eigenvalue is equal to 1. It doesn't expand it or contract it. And the same thing happens, as long as you're perpendicular, as long as you're along. But that's okay. That's a good solution, even if it just stays the same length. If lambda comes out to be 1, that still counts as a good eigenvector, as long as the vector doesn't rotate at all. So another way of saying is like, find vectors that matrix A doesn't rotate. That's another way of saying. Okay, but now here's the important point. So now this was just the definition of the eigenvector, and you say like, okay, well you just defined it that, and you just drew it here. Well, big whoop. What's the point? Well, now let's just take another vector. Say take another vector that's like this. Okay, well, I'll get rid of that one for the time being to make this a little simpler. Okay, so what does this matrix do to that one? Well, what it's going to do is it's going to sort of promote it, along a parallel line to this point on the ellipse. So what will that do to it? That one is going to rotate it a little bit, like that. So you can see, so this guy, when we operated on it, this guy rotated. And we knew that because we just solved for the one that doesn't rotate, and so now we're in one that actually does rotate. But notice it's heading toward the eigenvector. It's heading toward the nearest eigenvector. And if we had another vector like this one would get rotated even more. So this guy is going to be moved, to that position. So that guy is going to be actually rotated even more. So that guy got rotated even more. So that's why we like eigenvectors, because what they do is they say, if you operate this matrix on a vector, if the vector is in the direction of an eigenvector, it's just going to grow, like as in a weight pattern, get bigger. But if we operate it on something that's not in the direction, if we start off with a weight vector that's not in the direction of an eigenvector, it's going to rotate it toward the direction of the eigenvector and make it bigger. So that's exactly what we want to know. We want to know, like, what vectors do we get out of this equation when we run it repeatedly. Now you might be thinking, this is also abstract, so vectors, how does it relate to any kind of real life thing? So what is an example of a weight vector? How can we get a weight vector? So let's have an example of a weight vector. So I'm drawing it out as a matrix, but this is a weight vector. So how does that work? So say we had a weight vector that was like a center surround structure. And so that means, say it was positive over here and negative and maybe 0 over here. So if we cut across that, what does it look like? Well, at that line, it sort of looks like negative, and then it goes positive, and then negative again, and 0. Okay. Now, how is that a vector? It looks like a matrix. Well, what we can do is we can just say, let's just take all the lines of that. So say we had, say, 16 by 16. So let's take all the lines of that, and then just string them out like this. So that, 16, 16, 16, 16, up to, there would be 256 numbers. So there'd be, 256 dimensional weight vector. Okay, so that's our weight vector. So what does it mean to scale and rotate that? So there's actually a very sort of concrete effect. If we rotate it, if we scale it, so say the weight, I'll just do it in just, one dimension, just like across one line. But if we scale, so like what does the matrix do to just one line of that vector? So if we scale it, so here's what we start off with. If we scale it, it won't change the shape. It might make it a little bigger, but it won't change the shape. So that's basically scaling it. So this is scale. But if we rotate the vector, so that was the scale part. But if we rotate the weight vector, so this is right about, so scale, weight, vector. if we rotate the weight vector, it'll change its shape. So say it might go from something like that to something that, say, looks, something like this. Sorry, I don't want to go all the way down. Make it wrap around. Okay. Okay, so that one was rotate weight vector. And so now you can sort of see how it just relates to, like, say, center surround. So so what we're asking is, like, what is the shape of this guy? When we rotate by doing an update, it's changing the shape of it, changing it from something, say, like this into this. If we just scale it, it looks like that. Okay, so but that didn't mention, what is this thing here? What is the matrix of correlations? So that's a little hairy to describe, but that's the last thing we're going to do. And so the matrix of correlations, so here's the matrix of correlations. So this is our Q. So that guy's a matrix. So the problem is we have correlations across an image. And so, if we've got say here's an image and here's a face in the image, so, we know that, say, if, so it's an XY image. So here's the XY grid of pixels. And so what we're saying is that in images, it's typical that this pixel right here is correlated with this pixel. So those guys have a good correlation. So how do we represent that in a correlation matrix when this thing's already 2D? And so we just do the same thing here. So what we do is we unwrap the image, so here's the image unwrapped. So we just take that image and then just take all the lines out of that image and then paste them along this side of the matrix, and then just do the exact same thing down this way, ... So basically this will have, as many columns as image has pixels. And this will be a diagonal matrix because if we go to, say, some line up here, up here, say at that point, and then say, like, what is the correlation between, something up here to, say like the mouth down here? That'll be like the correlation with something down here. So that point will say, like, what is the correlation with the mouth and the eyes? And there'll be a number there, like, 7. And so this is going to be, if we then look at the mouth on, on the horizontal axis, that's going to be the same. These two guys will be the same. So basically it would just be a mirror image across the diagonal. And so what is that mess? That's called the covariance matrix. So, and what we can do is we could just take a face and turn it into one of these covariance matrices. It would just say which parts of the face were correlated with itself. The eyes are going to be correlated with themselves, but let's say the forehead is going to be correlated with the cheek. So there'll be a single number for each possible pair of points in this image, and you'll fill in this matrix, and then there'll be a mirror image of it. So you only need the actual sort of a triangle of unique numbers, and then these will all be the same. But so you could say, well, that's it's not very interesting for one face. Aren't you trying to recognize multiple faces? But what you could do is you could calculate a covariance matrix for a whole bunch of images and average them. That's really what a covariance matrix is. So put a whole bunch of faces in there, one at a time, calculate, how much are everything correlated. Put another one in there, how much are everything correlated. Average the whole mess, and then you end up with a covariance matrix of a group of faces. So once we have that, then that's what this thing is. Now we have this guy. And so now we can just say, well, why don't we just run this equation? We could start off with some random weight vector, run the equation, update the weight vector, run the equation again, update the weight vector, and see what we get. And then try a different random set of weights. Do that again. You could do that tens of thousands of times to try to get an idea of what is all the possible weight vectors you might get with this kind of correlation pattern. Or you could just solve the eigenvalue problem. And so if you solve the eigenvalue problem, what is that going to give you? That will give you what are the directions that the weights tend to grow in. But not only that, it will tell you these are important directions, because if you start off with a weight pattern that's not in the direction of an eigenvector, and you operate on it with this matrix, it's going to rotate it toward the eigenvector, which means that the eigenvectors will define what are the popular weight patterns that you're going to get out of this covariance matrix, which is, out of this sensory stimulation. And so if you do that, what you can find is that, one of the eigenvectors that you get out from using a center surround, so this, a center surround type correlation pattern is, something that looks like this. So you get, you basically get, something that's, say, positive and negative and positive. So you get like you can basically, we'll put another little positive over here. So you can basically get a pattern like that. So that's a weight vector that is orientation selective. And it turns out it's basically one of the first eigenvectors, the one with the biggest eigenvalue. So like one of these guys. And so what that's saying is that this kind of a correlation that is kind of a center surround correlation, when applied to tens of thousands of different random vectors, on average is going to generate something that looks like this, that's oriented in some particular direction. And so this, why did people do this? Well, what they did is the original papers from Linsker demonstrated the property that you can get these kinds of orientation selective units if you apply a center surround structure. But that was done in a bunch of simulations. And so by doing this kind of analysis, which was done later, to kind of simplify the problem, realize it's actually like a simple differential equation, which says, change in something equals some operation on something, not the change. And since this guy represents the change in this, you've got to feed it back in the next time you run the equation. That's a differential equation. By simplifying that and then doing eigenvectors on it, you can actually figure out what is the actual weight patterns that you're going to get. And so you could try that. The thing is, it's a very general way of doing it. So you, instead of just doing 10,000 simulations with faces, what you can do is you can essentially calculate one of these covariance matrices for any stimulus set. You can just get a bunch of landscapes, calculate the covariance matrix, and then once you've got that, just figure out its eigenvectors, and then you'll know what kind of weights you would get out of this correlation pattern. So I went a little fast, but it just gives you an idea of how you can think about these things, which is to really sort of strip it down to a very simple set of linear equations, which is what this is. And then once you've got that, you can take your pattern of correlations, your covariance matrix, do the eigenvalue problem, and then figure out what weights you're going to get out of that without actually simulating it. Now, I'm not saying that you shouldn't simulate. This is a very simple system, and a lot of times as systems get more and more complicated, you can't leave too many of these things out, and you have to simulate it. And so I'm not saying that you shouldn't simulate, but I'm just describing how you can sort of go back and forth between numerically simulating something, versus trying to apply simple mathematics that we can relatively easily understand to try to get some idea of what is the whole possible catalog of weight patterns they're going to come out of a particular covariance matrix. Okay, so I think we'll stop there, David, and then take some questions.